Oh, it works. Thank goodness. Okay. Okay, so hello. So how a couple notes how it's gonna work. I can see the YouTube chat, but it would be much easier for me to answer questions through Discord. So I'm also in the IEEE Discord, tutoring room 1. So you can ask questions there as well by joining it and then muting me. If you don't know what that is, I don't have a link, so I'll find one. This is for Dr. Fahimi's class, right? Or did Dr. Fahimi tell you guys about this? He didn't respond to my email, so. I also think Dr. Fahimi has a test review like at 4, right? Someone else told me about that, which is unlucky. But yeah, hi, I can hear you. Yes. The stream cannot, but oh, I hope it wasn't because of me. Oh, I canceled. Okay, well, and hopefully more of you guys show up. Okay, so in that case, I have some questions for you. What is covered on your midterm? I don't know what topics exactly are covered, or what up to what topics. So it'd be nice to know, because it varies between classes. Anybody? Yeah, you can post questions on tutoring there as well, though. Although, if you are writing something, I prefer it in YouTube chat, so I'll have that pulled up, not the Discord. So you can. I just probably won't see it. Up to what theorem? So here's what I'm guessing, Zeller. You're gonna be. Oh, substitution theorem. You mean superposition? So this. Yes, okay, so it covers up to that. Okay, so here's my plan currently. And tell me if any of this is something you haven't seen yet. So 1, I'll go over some basic circuit elements. Very basic stuff. And then 2, resistor networks. So that's, that's KCL, KVL, etc. 3, I'll go over node voltage. Mesh current. 5. And 5, I guess, would be superposition. Now, to clarify, have you guys done source transforms yet? Yes or no? The source transform and the Thevenin equivalent are also stuff that is usually covered on the first midterm. So it looks like you guys are getting to this on Monday, but I'm not sure about these two. Okay, no, I won't. Well, I will revisit these, and once I finish all this. Yeah, I mean, I'll start it, and if it doesn't look familiar, I just won't do it. Those are near the end anyway. So let's start off with just a review over basic circuit elements. So what makes up our circuits as an introduction? So basic stuff. What are we interested in? We're interested in voltage. We're interested in current. We're interested in power, measured in watts. Some interesting, so let's talk about power a bit. The passive sign convention. If you have some terminal with some voltage across it and some current entering the positive terminal, this is positive power. If you have the opposite with some voltage across it, current entering the negative terminal, this is negative power. This is the passive sign convention, and it's completely arbitrary. This is what we use. So positive power means you're absorbing power. Resistors always absorb. So you should never get a resistor delivering power, right? If you get a negative power resistor, you did something wrong. And negative power means you're delivering. So this would have to be a source in your case. And if you take a total network and add all the power in the network, it's going to sum to 0 because power must be conserved. Okay, so speaking of these sources, what are these sources? So there's 2 sources and 2 variants. So for voltage sources, we have the independent source and the dependent source. This is supposed to be a diamond, but my handwriting's terrible. And for the current, we have the independent current source and the dependent current source. The dependents are scaled by some factor in the circuit. The factor could be anything. And independence supply constants, voltage and current. So what's important to know about these things? An independent voltage source will give a constant voltage across the terminals regardless of what current's going through it. There could be any current going through it, and it will still supply V voltage. An independent current source will apply a current source across it no matter what voltage is across it. So you can have no voltage, you get infinite voltage, these things will still work. In the ideal case. Obviously in real life there are limits, but for this circuit analysis class, there are none. So this leads to something interesting. Let's see. I'll start some question and answer and see how that goes through this online format. If I have a voltage source, say V1, and another voltage source, V2, ground. If V1 equals V2, is this okay? Oh my lord. Can we do this? Yes or no? Okay, yeah, okay. And what if they're not the same? Then it'll be no. So, okay, so, yeah, so you guys can't hear the Discord. So someone said yes, and for V equal to V2, someone said no, V1 is not equal to V2. That's correct. So if these are correct, if they're the same, then we get some voltage up here. If they're not the same, the circuit blows up, literally, because if these are perfect, they force this node to be their voltage. But you can't have one node at 2 different voltage levels, so the circuit will probably self-destruct. Don't do this in real life; you will destroy your circuit. Similarly, for current sources, if I have 2 current sources in series, I1 has to be equal to I2. Otherwise, both of them are forcing different currents to the same branch. If it's not, it'll blow up. So just some things to consider about how these things work. I think there's actually questions about that in books, but no, not really tricky. So moving on to Kirchhoff's laws. Before starting that, let's define what a node is. So a node is a point where two or more circuit elements meet. And then a loop is a path that returns to its start without passing through a node more than once. Okay, so KVL says if you have some sort of loop, some voltage source, some voltage drops, that the sum of the voltages around the loop equals all of them equals 0, basically. You have to return to the same starting point, and then you have to use a sign convention too. So, for example, if there's a voltage rise here and a voltage drop here, they have opposite signs. So the convention I use is that voltage rises are negative and voltage drops are positive. So I say if I'm going around the loop this way, and for V1, that's a rising voltage, I'm going to call that negative. And then for V2, I'm going to see a drop in voltage, I'm going to call that positive. This is counterintuitive. It would be more natural to call voltage drops negative, voltage rises positive. But I use this because when you do mesh current or really any analysis, you're going to have more drops than rises. So it just makes the math easier. But you're free to use whatever you want as long as it's consistent. Similarly, so this is KVL. Similarly, for Kirchhoff's current law, you have some sort of node with currents going into it. The sum of the currents into the node, now the node is 0. And just like KVL, you need some sort of sign direction. So I choose to describe, and what I'll be using, is that the current going into a node is negative, and a current going out is positive. Oh no, sorry, I was about to say that's not what I use. I use the opposite. I use current going in positive, out negative. So this would be positive, this would be positive, this would be negative, is what I use. And you can use the opposite. Anything works. This is just what is more natural to me. So we can use these laws to solve resistor networks. You know, you can use KVL, and you can use this law in combination with Ohm's law. V equals IR, which gives a relationship between the voltage, the resistance, and the current across any resistor. You can combine resistors. So let's say you have two resistors in this configuration. These are called resistors in series because in between the two resistors, they have a node which only connects to those two. So if there was any other branch off this node, of anything, these would not be in series. The node connecting the two components has to only connect those two. They have the same current flowing through them, and you can combine them into equivalent resistance, which is the sum of the resistances in series. Similarly, we can have parallel components. Which connect to the same node at both ends. So we have one component here, a parallel component can connect to the same node at both ends. And to solve this, we can also make this a equivalent resistance with the formula of 1 over this equivalent resistance equals the summation of 1 over every resistor that's parallel. And this you guys should know. do you cover delta Y networks? So delta Y configurations. I know some teachers skip it. I'm not sure if you guys do. Okay, awesome. I hate them. Okay. And most of the ENA teachers tend to skip it. So what this is a fancy circuit configuration which has a unique way of converting. So a delta circuit looks like this. You have nodes, oh my god, what is that? You have nodes A, some resistance RA, A, B, C, RB, and RC. So this is called the delta circuit. And the Y circuit, or Y, or, you know, oh my gosh, Y, it looks like, well, a Y. A, we'll call this R1. We'll call this R3. And we'll call this R2. So this is the delta and the Y. And you can convert between them with the terminals A, B, and C being the same. So this is the same as this. This is the same as this. And then these are the same. So you can convert between the two. Because you can see they don't exactly combine in series or parallel like we normally would. And to combine them, there's a series of complex formulas. I mean, not complex, just tedious to memorize. So I hope you guys get cheat sheets if this ever appears. So for delta 2y, you can calculate R1 as equal to RB, RC over RA plus RB plus RC. And for R2, it's going to be RC, RA over RA plus RB plus RC. And then you can probably guess for R3, it's going to equal RA, RB over. And so if you know the delta network, you automatically know the Y network just by knowing all the resistors and which nodes they go where. You can also go backwards from Y to delta by saying RA equals R1, R2 plus R2, R3 plus R3, R1, and all that over R1. Then RB is the same thing on top over R2. And then RC is the same thing on top over R3. So knowing this, you can just flip-flop back and forth between these two configurations. And this is helpful in reducing some circuits when it otherwise wouldn't be possible by just combining things in series and parallel, because these configurations make things weird. They are useful if you're ever planning on like power circuits. This is where they're used. Power circuits, electronics, are when these things are actually used. So some other special configurations which you will see all the time is the voltage divider. The voltage divider, the principle is that when resistors are in series, the voltage will divide itself among each component to result in an overall voltage drop. And the current through all of them stay the same. So let's say I had some V plus here. It goes through RO. It goes through a bunch of other resistors. And it goes through RN. And then it goes to some V minus. So there's a voltage drop across these resistors and a bunch of them in series in between. If we want to find the voltage across any one of these resistors without using with just one formula, we can say that the voltage of any resistor, I, is going to equal to the total resistance, the total voltage across them times the ratio of that resistor to the rest of the resistances. And so in this case, it's going to be V plus minus V minus times Ri over R0 plus, plus all of them. So this is how you'd find the voltage across any resistor in the network. This is normally shown where there's two resistors in series. So you see it most often as this, right? Where you'll have R1, R2, and some V, and you'll say V1 equals, following the formula, the total voltage is V, then R1 over R1 plus R2. The resistor you want, the equivalent resistance. Same principle, just extended a bit. Likewise, you have the current divider. Current divider. And the current divider is for when resistors are in parallel, the current divides up, while the voltage across the components stay the same. So for some thing where you have an I total, some R, some Ri with a bunch of stuff in between they're not going to draw, and a final resistor Rn, they all accumulate over here. We're going to say, let's call this Rk actually, for being less confusing. So to define the current through any branch, where this is current total, Ik equals I total times the inverse relationship from voltage dividers. So now it's going to be the equivalent resistance over that specific resistor. So remembering our circuit divider formula, it's going to be this. What's that? In a special case that appears pretty often is like with the voltage divider, two resistors in parallel. So just two. Call this R1, call this R2, call this I. Call I1, I2. We'll say I1 equals I total times R2 over R1 plus R2. And then I2 equals I total times R1 over. And these will match with these if you do the math yourself. So those are the basics of circuit elements and resistor elements, and just basic resistor configurations and how to analyze them. Are there any questions over this portion? Next, we'll be moving on to the node voltage method. And this time I'll actually have some examples over node voltage, since I don't think you need examples over the prior stuff, but if you do, just let me know. Yep, we'll move on. Excellent. I should hope not. This should be the easy stuff, right? I'd be very worried if the people were confused over what a voltage is. Okay, node voltage. So, just to break it down, this is how I choose to approach node voltage problems. And it may be different from what the professors do. But I think one of the strengths of tutoring is seeing it from a student's point of view. So, okay, here are the steps I take. 1. Figure out where the heck your nodes are. ID nodes. Combine components when possible. 2. Choose one node as reference or ground. So choose ground. You can choose ground to be anywhere, but some places are stupid. You should choose ground to be in a convenient location that helps you out, rather than anywhere in the circuit. Usually this location is obvious. 3. You're going to write your KCL equations for each node in terms of the node voltages. How do I do this? As an example, let's see some resistor with VA, some resistance, and some VB over here. You are going to choose, because when you start out in a circuit and you don't know what V and what VB are, you have no idea where the current's going. So you're going to arbitrarily choose where the current's going. And it doesn't matter if it's actually going that way. You're just going to just choose it and stick with it. So I'm going to say I is going this way. And then to describe I'm going to say that I equals the change in voltage over R, and the change in voltage in the current direction. So from VA to VB, it's going to equal VA minus VB over that R. And then this gets you your system equations. And this order depends on where I define the current is going. If I said that I was going this way, this new I would still equal a change of V over R, but it will equal VB minus VA over R. It doesn't matter which one you use. They're both valid. Just don't change it mid-problem. And then once you've done this, you're going to solve the resulting system equations. Each node voltage. Because node voltage will get you the node voltages, obviously. And then if you have, as a little bit of addendum, if you have dependent sources, you want to express each dependent source in terms of node voltages, and then solve. And then you can still solve system equations, just without worrying about those pesky dependent sources. All right. So let's do an easy example, and then we'll do a hard one. And that's how I usually do these. I'll have one easy example and then one hard example, and I'll just run through both. Okay, here's a circuit. 12 volts here, 100 ohms. Oops. Whoever's unmuted, if you can mute yourself in the Discord, I can kind of hear an echo. Okay, so this is the problem, and the problem, I don't have a problem statement, but basically find node voltages. Using node voltage method at some point. So to start, my step one, if we remember, was to ID the nodes and combine components. So I'm going to do that. I'm going to say, okay, here is node A, here is node B, here is node D. I'm going to combine these two resistors over here into one because they're in series. So I'm going to make this 400 ohms, and I'm going to get rid of this. And I'm going to call this node node C. And then I'm also going to draw my currents in. So I'm going to arbitrarily state that I1, I'll make pink so it stands out. I1 is going this way, I2 is going this way, and I3 is going this way. Is this physically possible? No. Does it matter? Also no. So now we can start solving. Step 2 is to choose ground. Where should we choose ground for this circuit? You can choose it at any node, but you want to make a smart decision here. Yeah, thank goodness. All right. Yeah, node D should be ground, right? If you didn't pick node D, you should reevaluate your choices because it will make your life much harder. Okay, so now let's write our system equations for each node. Step 3. Let's look at node A. So looking at node A, there's a voltage source of 12 volts between it and ground. That means that means the voltage at A must equal 12 volts. That's great. Super convenient. There is no need to even write an equation. Let's look at node B. Node B, we have no idea what it is. So we're going to write its KCL and then convert it into the voltages. So KCL at node B, based on the currents I defined, is that I1 plus I2 plus I3 equals 0. Well, we can turn I1, I2, I3 into something that depends on the node voltages. So let's do that. So I1 is going to equal VA minus VB over its resistance, which is 100 ohms. I2 is going to equal VC minus VB over its resistance, which is 400 ohms. And then I3 is going to equal VD minus VB over that resistance, which is 200 ohms, right? And this all equals 0. But we know some of this. We know, for example, that VA is 12. We know that VD is 0. So we can further simplify this into some yes, sorry, I see a typo in my notes. 12 minus VB over 100 plus VC minus VB 400 plus negative VB over 200. So for node C, similar to node A, we can see 6 volts up here. This voltage source provides 6 volts between ground, and this node is node C. So node C just equals 6 volts. Which means that we can turn VC here into 6 volts. And then we can see that this equation has its one unknown, which is VB. So after doing the math, using whatever technique you want, you're going to find that VB equals 54 over 7 volts. And then that'll be our answer. So we found VA as 12 volts, VC as 6 volts, and VB as 54 over 7. And then that's the conclusion to our problem. And VD is 0, I guess. But, you know, that's not really relevant. All right. I'm just going to move on. If you have any questions, feel free to interrupt me. So, example 2, the harder one. Okay, let's say the circuit looks like this. I need more space. So here's our circuit. Not very friendly, but you know. Okay, so here's the circuit, everything defined. I don't think I forgot anything. And so the question is, as usual, find the node voltages. So it's scary, but we're going to start the same way. So first, we're going to define our nodes using some arbitrary system. I'm going to arbitrarily say A is here, B is here, and this is because that's how I wrote down my notes. But it probably makes more sense to do it the other way. D is here, and then E is here, right? We're going to define, first of all, E equals G, because, you know, it should be. And then we're going to draw occurrence. So I'm going to say that this is I1, I2, I3, I4. These two branches already have currents defined. Oops. And this branch also has its current defined. So we have currents for every branch now, in some way, shape, or form. So now the step now is to start. We have these dependent sources, the 3ix voltage source and the 2vy current source. We want to get these in terms of node voltages to make our life easier. So we're going to say that 2vy equals, okay, so what is vy in terms of node voltages? Well, it's the voltage up here minus the voltage down here. And that would be Vc minus Va. So now we have this current in terms of node voltages, which is great. So we can plug that in whenever we need to. Let's do the other way. Let's say 3ix. So what is Ix in terms of node voltages? Isa, no, you I'm not putting the screen in Discord. I'm doing it on YouTube. So you have to join you have to watch the YouTube stream. Okay. Ix, we can define in terms of up here. We want to define it in terms of node voltages. So we can do the same equation you've been doing. Let's say that Ix equals VE minus VD over 2, which makes sense, right? VE is 0, so this equals negative 3 VD over 2. So now we have both very dependent sources in terms of node voltages. And we can sub those in at the end to make our equation solvable. Let's start with node A. Looking at node A, we have negative 9 amps going away from it. We have 9 amps going away, so negative 9. We have I1 going into it, and we have I4 going away from it. And this is going to equal 0. We can define I1 in terms of node voltages as Vc minus Va over 2, and I4 as Va minus Vb over 1. And this will equal 0. So here's Va and here's Vb, and then it all works out. Okay, so also the same thing for node B. For node B, it's going to be I4 going into it, plus this current source going into it, so that's 2Vy, minus I3, and because I3 is going away from it. This can be written as I4 is Va minus Vb over 1. We know from our work up here that 2Vy is 2 times Vc minus Va. And we also know, well, we don't know what I3 is. So I3, normally you would define I3 using the resistance over here and Ohm's law to get us something in terms of node voltages. But we really don't know what it is, right? Let's leave it as I3 for now. And we'll come back to that. Let's look at node C. We can see that C has a 2 voltage source in which it and ground. So C has to equal 2 volts. Let's look at node D. Node D has I2, I3, and Ix going into it. So we're going to say it's I2 plus I3 plus Ix. We can write I2 as Vc minus Vd over 1. We still don't know what I3 is. And we can write Ix as negative 3 Vd over 2. And is equals 0. So now we have all of our equations. When we plug in Vc, that should be 2 volts. we're going to end up with 3 equations. So the equations for A, B, and D. Well, we get 4 unknowns, right? Because we don't know VA, VB, VD, or I3. To get rid of that, we need one more equation. So we can find a relationship between VD and VB as VD minus 3IX equals VB. Now, where did I get that from? Just looking at the circuit, we can say VB is VD minus whatever this voltage source is, which just happens to be 3IX. So when we plug all it in, we get the relationship of 5/2 VD equals VB. So here's our 4th equation. So now we have 4 equations, 4 unknowns, and we're going to solve eventually using math, which I will not show. VA equals -2, VD equals +2, and you can get everything else from there. So I skipped over all the math involved, but your equations are all here that we found from KCL. Any questions over this problem or node voltage techniques in general? And if not, I will move on to mesh current. Okay, we'll move on to mesh current. Okay. So, like before, I'll talk about the steps I like to use to go over mesh current. Steps. So, first step, ID your meshes. So figure out where your meshes are, and then also simplify if possible. Step 2. Like before when we defined our node voltages, we need to find our mesh currents. So we're going to find. Now, you can define them in any direction, but they should all go counterclockwise or just clockwise. It doesn't matter which way they go. They can be going this way or this way, but make them all go the same way. Step 3 is now we're dealing with KVL equations for around each mesh in terms of the mesh current using Ohm's law. So before we were doing change in voltage over I. Now we're doing change in current times R. Let's do an example for that. Let's say you have some sort of R here. It has some voltage across it, V. We have 2 mesh currents, I1 and I2, going here. Describing the voltage across R in terms of mesh currents. Voltage equals a change in I times R, which equals I1 minus I2 times R. Why I1 minus I2? Because we're picking the left mesh as our point of reference. So if the left mesh is our point of reference, that means I1 is positive and I2 is going the wrong way, according to the voltage drop. If we chose the right mesh as reference, it will be switched. We will get that V still equals a change in I times R, but it will be I2 minus I1 times R, because now, from our perspective, this seems like the positive way. Does that make sense? So this is the part most people will get confused by mesh current, I think. Why we switch it. Then step 4, solve system using whatever you want. And then like before, as an addendum, if dependent sources exist, and hope they don't, express in terms of mesh currents, and then solve as normal. Okay, let's do an example. And both examples are pretty easy for this one, but okay. Okay, so the question is, if I define these mesh currents going counterclockwise, how will they change? Okay. So, no, it wouldn't change. What matters for your equations is which way you define the voltage across the resistor as positive. And that changes depending on which mesh current you're looking at, right? Because resistors have to always drop. So resistors, they have to always drop current, right? Like remember the passive sign convention? Resistors always have to have positive power, right? Which means the current has to always enter the positive terminal. So if we choose the left mesh as reference, that means a positive terminal would be here. So it would still be I1 minus I2. Because I2 is going the wrong way. Because now I2 is going this way, right? Against our new convention. So you get the same equation. Does that make sense? Okay. No problem. Alright, let's do our example. We have 2 amps also, if you can't read something, which is highly likely, please tell me. This is terrible. What is this? Let me redraw it. My handwriting is questionable, so if you can't read something, don't worry about it. I will clarify if you ask. Let's draw our meshes. Well, okay, first let's identify meshes. In this case, it's very obvious. It's the squares, right? The 4 squares are our 4 meshes. Drawing our mesh currents, I'm going to draw them going clockwise. Because that's what I'm used to. Call this I1. Call this I2. I3. Ooh, I3. And then I4. You should also define ground. Should be down here, right? Well, that's less important because it's all about loops, not about voltage drops. So now let's use KVL. At mesh 1, looking at the mesh, without just qualitatively analyzing it, we can see that as our mesh current goes around here, it runs up this path. At this point, the mesh current has to be equal to that current source. And we know the current there. It's 2 amps. So we can immediately say I1 equals 2 amps. Write an equation for I2. Looking at I2, let's follow it. Let's look at the 2 ohm resistor first. 2 ohms times I2 minus I1, because they're opposing each other on that side. Now let's look at the 4 ohm resistor, plus 4 times I2 minus I4. The 3 ohm resistor, I2 minus I3. This equals 0, right? For I3, just like I1, we have I3 running right next to a current source. Except this case, it's the opposite way. So instead of knowing that I3 equals 4 amps, we know that I3 equals negative 4 amps. For I4, applying KVL around it and using our voltage drop method, we can say that across that 1 ohm resistor, it's going to be 1 times I4 minus the 4 volts from this voltage source up here. Remember that I defined voltage rises as negative in KVL. Is how I do it. And this is why. Because you do a bunch of resistor drops and then like only a couple rises. So it just makes everything easier. So that's where the negative 4 is coming from. Then looking at the 2 ohm resistor up here, we're going to add 2 times I4 because there's no opposing current. And then the 4 ohm resistor at the bottom is going to be 4 times I4 minus the opposing resistor I2. That equals 0. So after plugging in the values for I1 and I3 into the other equations, we'll have 2 equations, 2 unknowns. When you solve, you're going to get that I2 equals negative 0.85 amps and I4 equals 0.085 amps. And then you could do this math yourself. But you get the same answers. All right. Moving on then to something slightly harder. Not really. Example 2. Okay, so here's our circuit for problem 2. Same thing, find everything using mesh current. So like before, we're going to identify our meshes. 1, 2, 3. We can't combine anything, nothing in series or parallel explicitly. So we'll just start drawing our mesh currents. Say I1, I2, I3. I don't know why I made that one lowercase. I3. But we had dependent sources. So like we did with the node voltage one, we want to put our dependent sources in terms of mesh currents. So let's look at the 9 I delta. Well, what is I delta? I delta is the current running up here. When I2 gets over here, it's the only current running in this direction. So I delta has to equal I2. So 9 I delta equals 9 I2. A very nice simplification. Let's look at another one. We have the 1.7 V delta coming from this voltage source over here. What is V delta? Well, V delta is the voltage dropped across this resistor. If we want to put it in terms of mesh currents, we can use Ohm's law. V equals IR. What's the current? The current going through it is I1. Right? And only I1. So this can equal 1.7 times the resistor to I1, which equals, that's a terrible 3.4 I1. So we have both dependent sources in terms of mesh currents, which is excellent. Now we can write our equations for each of our meshes. So for I1, we go up the voltage source. It's a rise in voltage So I put a negative 50 plus 2 ohms times I1, since it's the only thing there, plus 4 times I1 minus I2, and then plus 9I delta. Now, this is a voltage source, but I'm putting a plus here because in the direction we're going from negative to positive. We're dropping voltage, not adding, right? So it's going to be a positive in my KVL equation. Does that make sense? Moving on for I2. There, and I can see it. Same thing. We're going to say, start with its 5 ohm resistor at the top. 5 I2 plus the 20 ohm resistor going to the right times I2 minus I3. Oh, okay. Another typo. Wonderful. Minus 9I delta in the voltage rise over here. Plus 4 times I2 minus I1. That's going to equal 0. I3. Looking at I3, we can see that I3 in this branch is the exact same as this dependent current source. So I3 has to equal negative 1.7 V delta. Negative because we're in the opposite direction of the current source, but the magnitude is the same. So when you plug in the values of the dependent sources, you're going to get two equations, the ones for I1 and I2, with two unknowns, also I1 and I2. When you solve using your favorite system equation method, you're going to get I1 equals negative 5 amps and I2 equals 16 amps. If you'd like me to solve it, I can, but math is math, so it doesn't really matter, right? I mean, it does matter, but there are many ways to do it. All right, so that's mesh current. If there are no more questions on mesh current, I'm going to move on to, oh wait, are op-amps on your test? I just saw that in the YouTube chat. I had read the first two words, but not the last one. Op-amps, yes, no, maybe so. Okay, I'll go with them anyway. Oh, okay. I see a question on how did I get 1.7 V delta. That's in the problem. That's what this current... I'm sorry, say that again? .7 V delta is from this current source. It was in the problem. That's where it came from. And then V delta was defined as this voltage. Okay, so I can do superposition. So that was the end of the stuff I know it's going to cover. I'll do op-amp since you guys covered this week. And you guys seem to not heard of the Thevenin source transformations, etc., etc. So we can just start with some simple op-amp problems and then go from there. So, op-amps. Well, first of all, what is an op-amp? An operational amplifier is a device that amplifies the difference between their positive and negative terminals up to its voltage rails. So, a nice big magical triangle that has some voltage here. Oh my god, that's not minus. Some voltage here, some voltage here, and it has rails or its power operations, and it has a V out, right? So in this class, we make some simplifying assumptions, right? We assume it's an ideal op-amp. If an op-amp is ideal, it follows two golden rules. Golden rule number, actually, it's probably hard to see, right? Oh, no, that's perfect. Golden rule number 1. The current into the terminals is 0. We're going to assume infinite input impedance. So we're going to say that I plus equals I minus, which equals 0. Golden rule number 2. The voltage difference between the terminals is 0. And that basically results in V plus equals V minus. So, to solve these circuits, you want to, 1, apply the golden rule, both of them, golden rules, and then 2, node voltage. This is how I do it. So I'll apply the golden rules, and then I'll immediately use node voltage analysis to find the output using the golden rules. And then that's it. That's how I approach every problem. All right, let's do an example. I mean, you could also memorize the configurations, but I think it's better to know how to do the problem rather than guess. So, example 1. Let's say we have a voltage source, a nice triangle, oh, too far up. Okay, so here's the circuit, and the question would be find I/O. Oh, what is I/O? This is I/O. Find that. Well, the first and easy step is if you find the output of the op amp, you find I/O using Ohm's law. I don't know why I couldn't think of the word ohm. So let's find VO. Let's analyze the op amp. So step 1. Well, first. We want to, before we can apply the golden rules, we have to know what's happening at the op amp terminals. This plus terminal and this minus terminal. What's happening here? So let's find out. So at the plus terminal, let's write a no voltage equation. You could do that, or you could actually no, so let's do the whole thing actually. Let's write the no voltage equation. Sorry. I see what I was trying to do here. Let's write it. So we have 6 minus V plus over 10,000 minus I plus minus V plus minus 0 or 5,000. And we get that from KVL and no voltage. We did that before. However, because of the golden rules, we know that I plus is 0, right? So we can get rid of that. At the negative terminal, we can write KVL or node voltage as negative 5 minus V minus over there's a typo. This should be 25 kilo ohms. Either I made a mistake with my notes, or I don't know how I did that. Let's say that's 25 kilo ohms. So 25,000 minus I in the minus terminal minus V plus minus V out over 6,000. That equals 0. So applying the golden rules again, this is 0, but also V plus equals V minus. So that means we can solve for V plus real fast. Because I minus equals 0, this equation only has one variable, right? So solving for V plus equals 2 volts. An alternative way you could have done this is just by using voltage division. So if you recognize that there is no current going to the positive terminal of the op amp, that means the resistors are in series, which means you can use voltage division. So you could also say that V plus equals the total voltage, 6, times 5,000 over 10,000 plus 5,000, and you'd get 2 as well. So both methods will give you the same answer. So because V plus is 2 volts, this also equals V minus according to our golden rule, right? So plugging that into our equation for the negative terminal, we're going to get that negative 5 minus 2 over 25,000 minus 2 minus V out over 6,000 is going to equal 0. And then when you solve that for V out, because it's now the only variable in the equation, you get that V out equals 16 volts. Okay, so V out equals 16 volts. That means we can easily find our current as I naught equals V out over the resistance, which equals 16 volts over 8,000 ohms, which equals 2 milliamps. And then that's our answer. So for any op-amp configuration, you can just apply the golden rules, apply node voltage, and you'll be able to find out what's outputting the op-amp. Okay, so I can do one more op-amp problem, or can move on to something else. Any suggestions? Yeah, so the other topics that you guys mentioned were Thevenin equivalents and source transformations and superposition. So there's 3 more I could potentially do. I mean, I could do all of them, but you guys haven't covered any of the higher level stuff, right? Like first order circuits. So no point doing that. So I think I'll move on to source transformations. And if you guys don't recognize that, tell me. And if you do, also tell me so I know I'm on the right track. Let's move on to source transformations. So if this looks completely unfamiliar and you've never seen this before in your life, then you definitely never seen it before. And we shouldn't do them. And if you guys haven't seen this, I doubt you've seen Thevenin. That'd be kind of weird. Okay, so let's say that we have some sort of circuit that looks like this. We have some voltage, we have some resistance, and we have them over some pair of terminals A and B. There could be anything over here. We don't care. It's just that it's over those terminals. We can turn this into an equivalent circuit that has the same effect upon those terminals A and B as some I, the same resistance, across those same terminals. And then you go between all these pairs with V equals I with Ohm's law. So this voltage equals this current times this resistance. And you can transform between them at will. Does this look familiar? Okay, you want that's good enough for me. We'll go through it anyway. So we're going to say that you guys have seen this before. It is very familiar. You guys all know it. So we're going to go through it very quickly. So a couple things to note here. One, looking at the left configuration, if we put a resistor in parallel between the voltage source and the resistor, like this, if we put if we put something like this across those same terminals A and B, R, V, and I'm going to call this blue R. It does absolutely nothing to affect whatever is between A and B. Because we'll notice that the voltage appearing here is still V. Right? So nothing has changed. Which means this can be reduced to just this again. Similarly, for the configuration on the right, a resistor in series with the current source does absolutely nothing because the full current still travels over here. Nothing's affected. So you can simplify this even further into this. Now, I'd like to stress here what I mean by simplify an equivalent circuit. What I mean by equivalent circuit, I mean equivalent over the terminals A and B. Nothing else. These have the same effect over those terminals, but if you get to talking about something else that's not over those terminals, it does not have the same effect. So you have to be careful with how you simplify circuits using this. But it's still a powerful tool to do your analysis. I have one example for this of how you just start going through and analyzing it. So let's do that one example. Let's say a circuit that looks kind of scary with a lot of sources, like this. You have here, and the question is, what is I/O? Now, you could do this using node voltage. You could do this using mesh current. But you can also do it using source transformations, which is arguably easier. So the first step to doing these source transformation circuits, and I realize I didn't write down steps for this, but you just kind of apply them. The first step to using source transformations is to identify what are your source transformation pairs. So you want to look for stuff that looks like any one of these two. On the resistance on the far right is 15 ohms. It was 15, 17, 5. I wrote 5 ohms twice for some reason, didn't I? Oops. Okay. So yeah, we want to look for stuff that looks like the two things up here. So we want a voltage in series with a resistor over the circuit, and we want a current source in series in parallel with the resistor over the circuit. So let's look for that. So first, I can see this. That is a current source in parallel with a resistor over the entire circuit. So there's one. I can also see this. This is a current source in parallel with a resistor over the circuit, right? Over these two terminals. There is also a voltage source in series with a resistor over some terminals. So we are seeing 3 source transformation pairs. So let's transform each one of them. The first one on the left, using Ohm's law, the voltage that I could transfer that into is V equals IR, to remind ourselves. So that's 6 times 2, that's 12 volts, right? So we're going to get 12 volts over here. And that has to be in series with its resistance, 6 ohms, over that circuit. So it's over the same terminal. So we're going to keep it that way. Let's see. I heard nothing? Okay. Sorry, I thought I heard something in Discord. Okay. 6 ohms. And then the 6 ohms from the circuit's still there. So I'm going to keep it there. The top source transformation pair, we're going to transform that into a voltage and resistor in series over the same terminal. So we're going to say it's a voltage and a resistor. And this voltage is going to be I times R, so 1 times 5, over the same terminals. So over these terminals. And then we're going to see on the bottom source transformation pair, it's going to be a current source and a resistor in parallel over those terminals. So it's going to be a current source and resistor in parallel with that terminal. So we have 17 ohms over here, and then we get the voltage, the current by V over R. 34 over 17 is 2. And then I naught is still over here, and we still have this 15 ohm resistor on the right. So what I did, I transformed, let's do some color coding here. I transformed this into this. I transformed this into this. I transformed this into this. Is that clear? Sounds like yes to me. And if it's not, stare at it for a bit, I guess. So now we can combine a bunch of things in series. This is the whole point of source transformations. So for us to be able to reduce the circuit. Because now we see that everything here is nicely in series. So we can combine voltage sources in series, if you did not already know that. Voltage source in series combine, current sources in parallel combine. So these voltage sources in series, we can combine them into one. 12 plus 5, 17 volts. These resistors combine to make 17 ohms. They are in series. And we still have that 2 amp current source, that 17 ohm resistor. Oh, that's more like a 12. And we still have I naught and this 15 ohm resistor over here. Right. But now we have now we want to reduce it. So now we can notice that this is another source transformation pair. So when we turn that into its alternative, we get 17 over 17, 1 amp here, 17 ohms here, and everything else remains the same. Right? And now we can combine everything in parallel. The sources combine in parallel, they add in parallel to make 1. So negative 1 amp up here. We get 8.5 ohms here. And we get 15 ohms here, and here's IO. So now we can easily find this using the current divider equation, right? So I naught equals I total, negative 1, times the opposite resistance over the one you want, 8.5 over 15 plus 8.5. This equals negative 850 milliamps, and that's the answer. So, as a summary, what we're able to do is we were able to reduce this whole circuit into just this, using source transformations and combining in series and parallel, which is the whole point of source transformations, to make your life easier in the long run. Are there any questions over source transformations? Any questions over source transformations or... Sorry, my laptop is running low on battery. Let me plug that in real fast. But yeah, any questions, concerns, thoughts, etc. Is the memory coming back over this topic? Or have you guys still never seen it before in your life? Sort of? Okay. I know Dr. Thevenin loves source transformation, so you'll probably see these, if you did cover them. Okay, so, in that case, I'll move on to Thevenin Equivalents, since it's a topic that builds upon source transformations. So Thevenin / Norton equivalents. Okay, so what is it? I'm going to talk about Thevenin equivalents, but Norton equivalents are a similar topic that you don't really need to know. You really only need to know Thevenin. So Thevenin's theorem states that any circuit's effect across two terminals can be reduced to basically just source transformation. So if you have a circuit, let's call it complex. Let's call it big mess of a circuit. Oh, that has some effect on terminals A and B. We can transform that into just some equivalent Thevenin voltage in series with some equivalent Thevenin resistance over the same two terminals A and B. So the theorem states that no matter what's on the left side, okay, so I see the question asking in the last problem, when I converted the 3-volt source at the beginning, how to turn to 2 amps. That's a 34-volt source, actually. Sorry if that was unclear. 34-volt source. And it converted 2 amps because I'm using Ohm's law. So V equals IR. I want the current. So V over R equals the current. And that's 34 over 17, yeah. Okay, so this is the Thevenin equivalent, and this is his theorem. And let's assume, and so the question becomes, okay, that's cool. How do we find these components? Like, we have this big circuit over here. How do we get this simple V Thevenin, R Thevenin, and the corresponding I Thevenin? You can source transform this, as we just learned, or just rediscovered, into an equivalent effect over the same terminals. Right. So here's our R Thevenin. I'm going to call this I Thevenin. And this is called a Norton equivalent. So if you have one, you know the other, basically. So how do I calculate these components? V Thevenin, I Thevenin, R Thevenin. That would be useful, right? So here are the steps to do that. To calculate V Thevenin, between the terminals, you're going to place an open circuit. Oh, that's not how you spell circuit. And then you're going to solve for the voltage across the terminals when they're open. This is basically simulating the max extreme of having an infinite load at the terminals. That V across is your V Thevenin. To solve for I Thevenin, you're going to place a short circuit between the terminals. You're going to solve for the current going through that short circuit, which is going to be equal to your I Thevenin. Intuitively, this is like having zero load at the terminals, right? So the whole point of Thevenin is it's saying that this equivalent affects any load at the terminals in the same way this big mess of circuit would. And here, you're basically saying, all right, well, if I have these extreme cases, then what would happen? And then you can solve for your V Thevenin and I Thevenin. Now, you can solve for R Thevenin using Ohm's law. So V Thevenin over I Thevenin equals R Thevenin. But you can also do it directly. So you can solve for R Thevenin by step 1. You're going to deactivate all independent sources. So what does deactivate mean? Well, deactivate means you're going to negate their effects. So for a voltage source, what a voltage source does is provide a constant voltage between two terminals. So to deactivate it, you want no voltage between those two terminals. So it's going to turn into a short circuit. If you have a current source, it provides a constant current through those two terminals. To deactivate it, you want no current. So that's going to turn into an open circuit. Your next step is to place a test source at terminals. That's not how you spell source. Once you place this test source, you're going to solve for the ratio of the voltage over current at the terminals, and that equals your Thevenin. And then something to note is that if there are no dependent sources, you can just speed this up by just finding the equivalent resistance between the terminals, and that'll be the same thing. But in general, this is how you do it. So any questions over? First of all, have you guys seen this before? And any questions over how you solve for Thevenin, Thevenin, or Thevenin, or what Thevenin equivalent is? All right, that's what to know. I'm gonna move on. So let's do an example over, Okay, so might as well just go over. So well, I'm going to do one example then. So here's an example. Here's the circuit that you're going to be given. Okay, and the question is, solve for I naught given any resistance R, so no matter what it is. You could, of course, do this using KVL and KCL, but it'll be a pain in the butt. So we're going to analyze it using the Thevenin's theorem. Thevenin's theorem states that we can solve for the effect of a circuit across any load by finding its equivalent. So so what we want is we want the effect of the circuit across the resistor, right? Terminals A and B. So when we do that, we essentially remove it from our equation and just find the circuit across. Just find the effect of the circuit across the terminals, and then we'll add it back in after we have found our equivalent. So I'm going to solve for all three, Thevenin, 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 independently. In practice, you would only need to solve for two of them, and you'd only want to find the third. But it's still a good check to solve the third independently, and just to know how to anyway. So let's solve for Thevenin. So to find Thevenin, if you remember, we're going to open the terminals. I'm not going to redraw the circuit. They look pretty open already, right? So let's find Vopen. Well, Vopen is going to be equal to the voltage across the 2 ohm resistor, right? We have conveniently have this current source here, drawing -1 amps. The voltage across the 2 ohm resistor can be found using Ohm's law, which is equal to IR, which equals to -1 times resistance, which equals -2 volts. So Thevenin equals -2 volts. This is okay, by the way. You can have a negative Thevenin. Let's solve for Thevenin. To find Thevenin, we're going to short the terminals. So let's scroll up here and let's short them. Let's say we have a short here, and we want to find this resistance, this current, I short circuit. Well, if these terminals are shorted, how much current goes down here? 0. No current goes down here. All the current from this branch goes into here, which means that the resistor gets shorted. And we can say, because of the current source, that I short circuit equals -1 amps, which equals Thevenin. So now here we could pause and we can say, all right, Thevenin equals Thevenin over Thevenin, which equals -2 over -1, which equals 2 ohms. So a couple of good things here. One, we don't have a negative Thevenin. That'll be a problem, right? And we solve for it. But let's solve for it independently to verify our work, and it's an exercise in how to do it. So to find our Thevenin, we deactivate our sources. Deactivating the voltage source gets a short, right? So there's a short here. This resistor was already there. Deactivating the current source gets us an open circuit. And then these resistors stay. A, B. There are no dependent sources, so let's just follow the current flow from A to B and try to find the equivalent resistance. Current goes in here. It can't go here because it's an open, so it has to go down here. If it goes here, it has no way to loop around, so it can't go here. So then it has to complete the loop over here, meaning the only resistance to the terminal C is this 2 ohms over here. They match, which is good. So our Thevenin does equal 2 ohms. So let's redraw our circuit now from the beginning. Now our Thevenin equivalent is saying we have negative 2 volts here, 2 ohms here, across the terminals A and B. That's the Thevenin equivalent. But the question was asking for what was the current I/O across any resistance R. So let's place it back in. Let's say, okay, now we have a load. Resistor R. And I/O was here. I naught is equal to V, the voltage across R, over R. Right. And this is equal to the total voltage, which is negative 2, over the total resistance, which is 2 plus R. So our answer is for any resistance R, the current I/O is negative 2 over 2 plus R, which we found by using the Thevenin equivalent across the terminals of that resistor to make it easier. And then Thevenin equivalents become more important in like electronic circuits when you're following for equivalent circuits across transistors and stuff like that, but it's good to know it now. Alright, any questions? Alright, I can do one more Thevenin equivalent problem because I actually have one more. Or I can move on to superposition. Any preferences? Okay, because someone requested it for one more Thevenin problem, and this one will be the harder one, obviously. Okay, so actually, let me just introduce superposition, see if it's familiar. The concept of superposition is that in these linear circuits, we can think of them as functions, right? Where your inputs are sources, and your outputs are the resistor network. Voltage, or your outputs are voltages and currents, right? Usually, in a circuit, you solve for each one. You solve for the whole thing at once, right? Every source active, everything going at once, everything input. What superposition states is that this can be broken up as essentially saying that you can deactivate elements of the circuit and then reactivate them later and deactivate everything else and add your two answers together to get the actual answer. And we can deactivate sources just like we did for Thevenin. And then we're going to add our separate answers together to get what would have been the original answer of the circuit. So that's what superposition is. All right. I'll actually just do that then, and if we have time at the end, then we can go back and do some more problems. So, superposition. superposition. Let me more formally introduce it. And by that I mean you read my notes. So for any of you people in signal systems, this should be something you know. Our circuits are LTI, linear time invariant systems. And so superposition is just a property of these LTI systems, which means that essentially the output of the system with all inputs applied at once is the same as each input applied separately and then added up. So like I said before, if our circuit is a function which has inputs as sources, we can look at the function or the circuit with just one or more of these inputs active, and then add them all up to get what would have gone if we had solved the circuit with everything active at once. So the steps to do this: you're going to deactivate all but one source. Then you're going to solve the circuit using whatever method you want for whatever output it's asking for. You're going to repeat 1 and 2 for a different source. And at the end, you're going to add up all answers to get your final answer. So this is convenient in cases where sources really get in the way. So to illustrate this, I have one example of an inconvenient circuit to solve without superposition. So the problem is, let's find Ix and Ix in the following circuit. Okay, so find Ix in the following circuit. So there are, of course, many ways you could do this, but I'm going to choose to do superposition. So I'm going to start by deactivating the current source. I want that gone. So I'm going to replace the current source with an open circuit to deactivate it. So this circuit, for our first step, becomes just this. With Ix here, because this is an open circuit now, right? Simplifying this, we can see that these two resistors are now in series. These two resistors are also in series, and everything is in parallel. So we can redraw this to make it more pleasing to the eye and make more sense. As these resistors in parallel to make 6 ohms. And 4 ohms are these two in series. And then everything's in parallel, right? And this is Ix. So using any analysis you want, we're going to call this Ix1, and it's going to equal 2.053 amps, right? So that makes sense. And so that's only part of our answer. Let's solve for this. Let's solve for the rest of the circuit, because we still have to solve for the current source. So let's deactivate the voltage source and activate the current source. So the current source goes up here. This is active. The voltage source turns into a short when you deactivate it. And here is Ix, we'll call it Ix2. This is slightly trickier to figure out what to do with. I would suggest using Kirchhoff's current law to find this problem. If you can find, oh, I don't know why I did that, sorry. If you can find this current and this current, I'm going to call this I2 ohms and call this I3 ohms. You can solve for Ix2 using KCL To simplify this circuit, I would suggest combining everything. But as follows. You can combine these two in parallel and these two in parallel. When you do that, you're going to get 1.33 and 0.75 ohms. Now, remember the end goal is to get I2 ohms and I3 ohms. So to do that, if I knew the voltages here, here, and this is ground, then I could find what the current is by using Ohm's law. So we find the voltage V1 minus V2. We find that equal to a negative 4 volts. And we find the voltage across, or we just find V2 equal to negative 2.25 using our analysis methods. So now, using KCL, we can say that Ix2 equals I of 2 ohms minus I of 3 ohms, which equals negative 4 over 2 minus negative 2.25 over 3, which equals negative 1.25 amps. So that's Ix2. But we want I of x in the original. So the principal superposition says, this principal superposition says, in this case, f, we had a function of current plus, we had a function of current source plus a voltage source, with our output of this function being Ix. What we were saying is, we can also have a function of just the current source equal to Ix2. And we can have a function of just the voltage source equal to Ix1. And superposition states that the function of current source plus voltage source equals the function of current source plus the function of voltage source. So Ix equals Ix1 plus Ix2, which equals, we found Ix1 as 2.053 amps. That's a 5. And we find Ix2 as negative 1.25 amps to make the final answer 0.8333 amps. And that's Ix. Solve using superposition to make our life easier. Any questions over how this was made or anything? Or the process or the idea behind superposition? No? Okay. In that case, the review technically has 15 minutes left, so I can take any questions. I think I've covered all the topics that may or may not be on your exam. So if you have any specific questions, I can answer them now. Or anything you'd like me to go over a bit more, I can do that too, as there are around 15 minutes left and the time allotted for this review. Or if not, I can just end the stream. Then we're good. I know from tutoring this class before, Dr. Fahimi's tests are usually free response and have some like tricky problems that make you think. But I can't really say much more than that because I did not take Dr. Fahimi. I took a different professor when I took ENA. And the question was, what will the test for being take-home look like? I can say that Dr. Fahimi does take-home tests in his regular class too, before coronavirus. I think his test 3 was always take home. So he's used to writing them. That's what I'm trying to say. So I wouldn't expect anything easy. Yeah. So any other questions? And if not, this is all recorded on the YouTube channel. I don't think it was advertised because you guys said Dr. Thevenin didn't mention it. So if you could maybe post a review in like in your group me or something, so people can actually watch it, that'd be great. And if I don't see any questions, I'm going to end it here. So thank you, and good luck in your exam. Yeah, good luck, everybody. And goodbye.